In this video, we'll define what it means for a function f to tend to a limit as x tends to infinity. We'll also define what it means for it to tend to a limit as x tends to minus infinity and as x tends to a real number. Remember from the video Limits of Sequences, we defined what it meant for a sequence to tend to a limit as n tends to infinity. We said a sequence yn tends to a limit L as n tends to infinity if, however small a number I chose, the sequence yn would get that close to L and stay that close. One of our examples was the sequence yn equals 1 over n. I can just plot a graph of this. So if I plot the points of yn, which was yn equals 1 over n, it looks like this. Start off at 1, and then at 2 it was a half, then it went a third. Now this sequence tended to 0 because eventually the points on this sequence get as close to 0 as I like. So however small a distance I choose, the points in the sequence will eventually get within that boundary from 0 and stay in there. Limits of functions are defined in a similar way to limits of sequences. If we have a function like fx equals 1 over x, where I've actually already plotted some of the points for this already, so I'll use it. If we sketch the graph, you can see that this function gets closer and closer to 0. In fact, whichever tiny distance we choose, like this distance I've already sketched in here, whatever distance we choose, this function will get within that from 0 and stay that close. If a function does this, we say it tends to limit 0 as x tends to infinity. If a function tends to 0 as x tends to infinity, we write it like this. We'll write fx tends to 0 as x tends to infinity, or sometimes the limit of fx as x tends to infinity equals 0. Here's another function with the limit. This time we'll have f of x equals 3 minus 1 over x squared for x greater than 0. So I'll just sketch this graph. We'll have 3 about here. Right, this graph looks something like this. Now again, whatever tiny distance I choose around 3, it doesn't matter how small this is, this function eventually gets trapped that far away from 3. So this function has limit 3, and again we write fx tends to 3 as x tends to infinity, or the limit of f of x equals 3 as x tends to infinity. In general, we say that a function has limit L as x tends to infinity if, however small a distance you choose, the function gets closer than that and stays closer than that as x gets larger. Not all functions have real limits as x tends to infinity. Here's one that doesn't. We'll have f of x equals x squared. And that, as I'm sure you know, looks something like this. Now, as x gets larger, this certainly doesn't get any closer to any real number. In fact, however large a number I choose, this function will eventually get bigger and stay bigger than it as x goes off to infinity. If a function does this, we say that it has limit infinity as x tends to infinity. We write f of x tends to infinity as x tends to infinity, or limits of f of x as x tends to infinity equals infinity. If we have a function like f of x equals minus x that looks like this, this also doesn't tend to a real limit as x tends to infinity, but it doesn't tend to infinity either because it doesn't get very large. In fact, however large and negative a number I choose, this function will get below that number and stay below it. If a function does this, we'd say it tends to minus infinity as x tends to infinity. So we write f of x tends to minus infinity as x tends to infinity, or again, limit of f of x equals minus infinity as x tends to infinity. Some functions don't have any limits at all as x tends to infinity. This is the graph fx equals x sine x. And as you can see, it certainly doesn't get closer to any real number as x tends to infinity. Also, if I pick a really large number, the graph will eventually get above it, but it won't stay above it because it'll always come back down to 0 and go negative. Also, if I pick a really large negative number, it'll go below it, but it won't stay below it because it'll go back up to 0 and then go positive again. So this function doesn't tend to infinity, and it doesn't tend to minus infinity as well. So this function doesn't have any limit at all. We can also define limits for functions as x tends to minus infinity. Here's a graph of e to the x. So this after 0 gets large, before 0 gets closer and closer to 0. As x gets more negative here, this function gets closer and closer to 0. And however small a distance I choose, the function will get closer than that to 0 and stay closer than that as x gets more negative. If a function does this, we say f of x tends to 0 as x tends to minus infinity, or limit as x tends to minus infinity of f of x equals 0. In general, we say a function has limit L as x tends to minus infinity if, however small a distance I choose, the function gets closer than that and stays closer than that as x gets more negative. If we have a graph like x squared, which I'll just sketch, you can see that this doesn't get closer to any real number as x goes to minus infinity. But however large a number I choose, as x gets more negative, this graph will go above that number and stay above that number. If a function does this, we say it tends to infinity as x tends to minus infinity. So f of x tends to infinity as x tends to minus infinity, or the limit of f of x equals infinity as x tends to minus infinity. Now a function like x cubed doesn't do either of these things. The graph is something like this. So it certainly doesn't get larger than any number I pick as x goes to minus infinity and stay larger than it, and it doesn't get closer to any real number, so it doesn't have a real limit. But however large or negative a number I choose, as x gets more negative, this function will drop below that number and stay below it, and this works for any number I can choose. When this happens, we say f of x tends to minus infinity as x tends to minus infinity, or again the limit of f of x equals minus infinity as x tends to minus infinity. Now again, a function needn't have any limit as x tends to minus infinity, and our graph of fx equals x sine x is a good example of this again. As x gets more negative, this certainly doesn't get closer to any real number, so it doesn't have a real limit. It might go above any number we can pick, but it won't stay above it because it comes back down and goes through 0. And it won't get more and stay more negative than any large negative number we can choose, because it will always come back up to 0 and go positive again. So this is a function that has no limit as x tends to minus infinity. There's one more type of limit we can define for functions. Let's look at the graph of a really simple function like f of x equals x plus 3. So that looks something like this, with 3 there. Now if I pick a point on this graph, like say here when x is 1, the graph goes through 1, 4, you can see that as x approaches 1, the value of the function approaches 4. We say that f of x, the limit of f of x, equals 4 as x tends to 1. Similarly, if we say x equals 5, then the function is at 8, and as x gets closer to 5, the function gets closer to 8, so the limit of f of x as x tends to 5 equals 8. Now this doesn't look very useful, but it does become useful if we have functions that aren't defined at a point. Now this is the case with this function. This is f of x equals x sine 1 over x. You can see for this function that as x gets close to 0, the function gets very, very close to 0. But because at x equals 0 we have a 0 denominator, this function isn't defined for x equals 0. But because the function gets closer and closer to 0, it's almost as if the value of the function at 0 should be 0. So the limit of f of x as x tends to 0 equals 0. And you can think of 0 as the value f of x should take when x equals 0, even though it's not defined. Here's another example. This function is f of x equals e to the minus 1 over x squared. Now again, when x equals 0, we have a 0 denominator here in the function, so it's not defined at x equals 0. But as x gets closer to 0, this function approaches 0, so again, the limit of f of x as x tends to 0 in this case is 0. And again, we can think of 0 as the value f should take when x equals 0. Not all functions have nice limits like this. If we look at the function mod x over x, so f of x equals mod x over x, if x is positive, then the top of this is just x, so this becomes x over x, which is 1. But if x is less than 0, then this becomes, well, the top becomes minus x, so that's minus x over x, so that's minus 1. When x is 0, it's not defined at all, so the graph looks like this. It's just 1 when x is greater than 0, and it's just minus 1 when x is less than 0. And you can see here there's no way we can define a good limit for this, because as we approach 0 from the right-hand side, it looks like it should be 1. But if we approach 0 from the left-hand side, the function looks like it should be taking value minus 1. So here it's not clear what f of x should be when x is 0, because there isn't a proper limit for this function as x tends to 0. So this is a good example of a function that doesn't have a limit as x tends to a number.